name is Matthew Keene, and this is my lab report on Lab 5. I chose the following Slinky lab. On this slide I have some of the fundamental equations that I used during this experiment. We have the velocity update formula, we have the Newton's second law with respect to momentum, so derivative of momentum over time. We have the force of a spring, so the K constant times the length that the spring is stretched times the L hat vector. We have the potential energy for a spring, so 1/2 times the K, which is the spring constant, times the change in position, so you have position final squared minus position initial squared, and you also have the energy formula, so delta K plus delta U, which is the spring potential energy, plus delta UG, which is the gravitational potential energy, is equal to the work of the drag force. So the purpose of this experiment was to analyze the motion of a spring system affected by air resistance and gravity. The result of this experiment was because the Slinky's center of mass changing as it compresses, the conversion of potential energy, both spring potential energy and gravitational potential energy, into kinetic energy causes the tension and the gravity forces to equal each other, which is why the Slinky moves the way it does, is because it comes to a constant velocity, and so it looks like it's not moving, but it still is. Above the results I have some of the code segments that I used. So I have my work and my force of tension, as well as my net force, which is the work plus the force of tension. I have the velocity update formula, the position update formula, I have my delta T, and then I also have my mass. It says ball mass, but it was spring, and that was equal to 0.218 kilograms, and my delta T was 0.003. And then my drag force, which is B, it's down here, it's equivalent to 0.524. So this is the setup. My system was the spring in the earth. My mass was 0.218, delta T was 0.003, and my B was 0.524. The B I calculated through trial and error, because we aren't given the exact formula for drag force, and because the velocity is kind of difficult to measure, I just kind of messed around with it until I got something that looked correct. And then I have my while loops, so while delta T is less than the length of the video, we're updating the work done and the tension force, as well as the net force, and also updating the velocity and position. So here are my computational models. So this was the change in position. You can see, sorry, not the change in position. I did not mean to write that. This is the force over time. With respect to the y-axis is the change in position, and this is the change in force. And here are my results for GlowScript. You can see that compared to the previous couple slides, this is a lot more smooth, and that's because, Tracker isn't the most precise, so when you're clicking, it's not going to necessarily be 100% perfect. The video is also old, and the quality wasn't the best, so the tracking of the motion probably isn't super perfect. The frame rate is not great, and also the mass of the spring is variable, and I wasn't able to account for this in the program, just because it would have been a lot of work on my part. So yeah, the mass is changing as the spring is moving down, because at some points it's in contact with the ground, and at some points it's in contact with the hand, and the coils are compressing on each other, so overall it's not weighing 100% the same. But yeah, that's it. Thank you.